Now let's move to the more interesting part of the ARM instruction set that deals with branch instructions. We need branch instructions to implement if statements, for loops, while loops, and almost any kind of program where we need to make a decision on the value of a certain variable. So ARM, like simple RISC, supports some very simple branch instructions. There are some complicated ones as well, but let's take a look at the simple ones. So similar to simple RISC, the format of every branch statement is the same, which is essentially a branch instruction and a label. So we branch to the label, we jump to the label, and the label is the first instruction at the branch target. So let's say if this is a program, and so there is a certain label .foo over here, and we branch to .foo. What this means is that the control gets transferred from here to here. So the basic and the simplest instruction is an unconditional branch B. So an example would be, let's say b.foo. It would jump unconditionally to label .foo. Similar to simple RISC, we have BEQ, branch if the flags indicate equality, and branch if the flags indicate inequality. So what I mean by flags is that the last instruction that set the flags should have had an equal to, should have concluded that both the values that are being given to it are equal. Only on that condition would this particular branch actually branch to this label. So the explanation is that we branch to .foo if the last flag setting instruction, so mind you this is one phrase, flag setting instruction, has resulted in an equality, and this will show up in the Z flag being equal to 1. Similarly, we'll have branch not equal to, which is just the opposite of branch if equal to, where the Z flag is equal to 0. So the fantastic thing in ARM is that we have many branch instructions, and all of them have a standard format. So we have B first, and then a branch condition code. So this is the format of the branch instruction, where we first have the letter B, and then we have a condition code for the branch, so one example of this would be BEQ, where EQ is the condition code equality, and the other would be NE, where NE is the condition code for lack of equality. So we have many such branches and condition codes. So we have actually 15 such condition codes that we shall see in the next slide. So first let's take a look at the condition codes that we have seen. So mind you, all of these are suffixes. So we'll have B plus this suffix. So it can be BQ, BNE, or BGE, or BGT. Any of these suffixes are allowed. So let's take a look at the first two, which we have already seen, BQ and BNE. So the first equality is when the 0 flag has been set to 1 by the last instruction that sets the flags, which we call the flag setting instruction. Similarly, the any flag not equal to flag is just the opposite of this. Now let's take a look at one more pair of conditions which are very interesting. So let's consider HS. HS means unsigned higher or equal. So what we do is that when we take two 32-bit numbers, we disregard the sign bit and think of them as unsigned numbers, and we compare them. So the way that we would compare any unsigned number A and unsigned number B is that we'll subtract B from A, right? So basically, given any two numbers, what we would do to compare them is that we'll subtract A minus B. If A minus B, if A is greater than B, which means it's unsigned higher or equal, then there will be no borrow, right? So the borrow will be false. So as a result, the carry bit will be equal to 1. So this is pretty much the condition that the hardware checks, that is the carry bit equal to 1. In this case, this particular condition is true. So the CS or HS, the opposite of HS is LO. So in this case, this is the first one was unsigned higher or equal, right? So basically greater or equal in an unsigned sense. The opposite would be less than. So in this case, the carry bit needs to be 0, or alternatively, when we do a subtraction of the form A minus B, we actually generate a borrow. And since the carry and the borrow have a reverse sense, in this case, the carry bit will be equal to 0. So there are again another pair of conditions, Mi and Pl, which means that A minus, so basically when we subtracted, the last result that came had a minus sign. So in this case, the negative bit would be set to 1. So this essentially says that the last value or the last result that the flag setting instruction considered had a minus sign, and so the Mi suffix condition would then be true. So the opposite of Mi is Pl, which is positive or 0. So the condition is also exactly opposite. Let's again take a look at the next pair of conditions, Vs and Vc. So Vs is the case when an overflow occurred. An overflow is a condition where it basically means that the final result could not fit within the number of bits that are available. So consider a 32-bit system, but let's say we multiply, the product of a multiplication requires more bits, more than 32. So in that case, what needs to be done is that we either allocate more bits or we signal an overflow. So overflow in this case would mean that the result cannot fit within 32 bits. So the overflow flag will be 1, and in the case of no overflow, the overflow flag will be 0. Now let's consider a different variant of HS and LO. So this was, mind you, unsigned higher or equal. This is just unsigned higher. So in the case of unsigned higher, we will have this condition, C equals 1. So this indicates unsigned higher or equal. But along with that, we'll also check that the 0 flag is equal to 0, which means that it is also unequal, right? So if, let's say, A is greater than or equal to B and A is not equal to B, then we can automatically infer that A is greater than B. Similarly, we can have unsigned lower or equal, which is just the opposite of this. So in this case, we'll also take this condition C equals 0, which means it's unsigned lower or equal, and also ensure have an OR condition that it is either less than equal to or it is just equal to. Oops, I'm sorry. Sorry. This is a mistake. Let me see. Sorry. So C equal to 0 denotes that number A is strictly less than B. So in this case, unsigned lower. So C equal to 0 means that if both the numbers are A and B, A is less than B. So C equal to 0. So this is either one condition or it is strictly equal. So if I combine the conditions, it is less than or equal, we have the condition less than equal to, which is exactly what it says, that the ls suffix or condition means that the numbers are if I am comparing A and B, A is unsigned lower or equal. Now let's consider some signed operations. So GE is signed greater than or equal. So in this case, I do the same thing. I interpret both the 32-bit numbers as signed numbers, and I perform a subtraction. If the final result is not negative, then we can say that the A is greater than or equal to B. And if the final result is negative, we can conclude that A is less than B. So this is same as saying that A minus B is less than 0, which implies The implication here is that if a minus b is less than 0, this means that a is less than b. So similarly, let's consider GT and LE, which is similar to the unsigned operands HI and LS that we introduced. So GT means it's signed greater than. So this alternatively means that the Z flag is 0. If the Z flag is 0 means that the numbers are not equal, and n equals 0, which means that the numbers are greater than and equal. So the same logic holds if A is greater than equal to B and A is not equal to B, then we can automatically infer that A is greater than B. And the same logic holds for sign less than or equals. If you consider this expression and this expression, they are equivalent. So the 0 flag needs to be 1, which means either there is equality or there is less than. And this is the condition for unsigned less than, and this is the condition for signed less than. This condition is actually a default, so as a result it's typically not required, which means always. So this same as an unconditional branch. So in the sense B AL is also the same as B, which means branch all the time. And the last suffix 15 is actually not used. It is reserved such that it can be used later when the instruction set is expanded. So let's consider a simple program first. That's maybe the most important. So let's write an ARM assembly program to compute the factorial of a positive number. Assume the number is large enough, greater than 1. The number is stored in R0 and save the result in R1. So let me give you 10 seconds to look at this particular program. Alright. So the first thing that needs to be done in any kind of an assembly program is that we need to do register assignment. So let's assume that the prod variable product is saved in R1, which is also where we need to return the result. It's initialized to 1, and the index of the loop is also initialized to 1 and it's saved in R3. So let's do one thing. Let's start. So since we know that the number is greater than 1, we can happily start with the multiplication and check later. So let's first do the multiplication, which is prod equals prod times IDX. So in this case, I multiply the index, which is in R3, with the current product in R1 and save it in R1. Then I compare the index with the input number. So the index is in R3 and the input is in R0. So I just compare them. I compare IDX with the input with R0. And then what I do is that I increment the index. So I increment the index, so I do IDX plus plus. So at this particular point, let's assume that the index is equal to num, right? Let's assume that we infer an equality and the index is equal to num. So since the index has already been multiplied into the product, we don't need to go for another iteration of the loop. So what we can do is that we can compare if this particular comparison led to an equality or not, because mind you, the add instruction is not setting the flags. So we'll only use the result of this particular comparison, and if this comparison to us indicates that the index is not equal to the number, then we need to go back to dot loop once again and loop for one more time. Otherwise, if we have reached the end of the iterations, when index becomes equal to the original number stored in R0, we can exit and the product is stored in R1. Alright, so now that we have seen a very basic program, let's try to make our repertoire of assembly instructions slightly more complicated by introducing the branch and link instruction. So the branch and link instruction is the same as, not the same, but similar to the call instruction in simple RISC. We use it to invoke functions, to call functions. So it works in exactly the same way. We jump to a label, and the label points to the first instruction in the function. So it does, so the BL instruction, branch and link, does two things. We jump unconditionally to the function at .foo, and we save the next PC, which is the current PC plus 4, in the return address register, which is also called the LR, which is actually called the LR register in ARM. So this is the return address register. This particular register over here is the return address register, and it's also called the link register. So this register will contain the value of the current PC plus 4. So let's write a simple assembly program with a function call. So let's consider a simple C program first. So let's have a variable x that we set to 3. Then we call the foo function that returns 2. So we add x plus the return value of foo, which is 2. So 3 plus 2 we get 5, which will be again be saved in variable y. So let's consider what needs to be done here. So the first step is always mapping the variables to registers. So let's map x to R1. Let's add 3 to it. I'm sorry, let's move 3 to it. Subsequently, we call the foo function. So the foo function moves 2 to R0, and so we need to return. So the interesting thing is that in ARM there is actually no return function. So this is the way that we typically return. Well, there are few more ways also, but this is one of the simpler ways. So what we do is that since the program counter and the link register, which is the return address register, are explicitly visible to the programmer, what we do is that we set the contents of the LR to the PC, which is exactly the same as returning, because LR contains a pointer to the next instruction, which is over here. So if we move the contents of the return address register, the LR register, to the program counter, it will be the same as jumping to the last instruction in the main function. I'm sorry, I shouldn't be saying the last instruction, is the instruction just after the function call in the main function. So in this case, R0 contains 2, so we are adding R0 with R1. Essentially, we are adding the return value of the function with R1 and saving it in R2, where the assumption is that the variable y is mapped to R2. So what is the important learning that we get from this slide? What we get to learn is that the link register, which contains the return address, is mapped, if we transfer the contents of that to the PC, which is also one of the registers that is exposed in our register file, this is the same as returning from a function. It's exactly the same. So we don't need a ret instruction. So let's now take a look at some another kind of instruction which is slightly easier, and nowadays programmers are preferring it. So this particular instruction is called BX. So BX, it takes a single argument, a single register. So the explanation is that, let's say I have an instruction of the form BX register R2. This means that I jump unconditionally to the address contained in register R2. So I can think of this as a variant of the B instruction, an unconditional branch, but the B instruction actually took a label and the BS instruction takes a register. So nowadays this is the preferred method to return from a function, and we actually don't use move PCLR. I mean, we are advised not to use this thing. So let me write it over here. Advised not to use. Well, this should be used in variants of ARM processors that do not provide the BX instruction. But if the BX instruction is provided, which is the case in at least most ARM processors, what we are supposed to do is BXLR, which basically means that take the address that is there inside this link register and jump to it. That's basically the idea. So instead of moving LR into PC, which is what we saw in the previous slide, a better idea, a much better idea is to use BX LR, where we jump directly to the contents of the LR register. So let's consider the same program with the BX function, with the BX instruction. So we have the first instruction, move R1 #3, sets X to 3. We call the foo function using the BL instruction, branch and link. So in LR register, the return address gets saved. We move 2 to R0, and instead of moving the contents of LR to PC, this is the new instruction, BX LR. And in this case, we branch to the point, to the address that is contained inside LR, which is the address of the next instruction after the function call. So let's now look at some conditional variants of normal instructions. So it is just not the case that these conditions EQ, NE, GT, all the conditions that we studied, all the 14 conditions, other than the AL always condition, right? So basically all the 14 conditions that we looked at, it is not necessary that they will only be put after a branch, right? So previously what were we doing? We were putting them after a branch, after the B instruction. It is not necessary. After a lot of normal instructions like add, subtract, multiply, we can suffix the conditions as well. So for example, we can have add, then we can have the condition EQ, or we can have add and we can have the condition MI. This will basically mean that the add instruction will only execute if the MI condition holds true, or the subtract instruction will only execute if the any not equal condition holds true. So these kind of instructions are also known as predicated instructions, which means that if the condition is true, the instruction will execute normally. Otherwise, the instruction will not execute at all. It is pretty much like a no-op. So let's take a look at a slightly more complicated example. So let's write a program in ARM assembly to count the number of ones in a 32-bit number, which is stored in R1, and let's save the result in R4. So let me consider a 4-bit number. So consider a 4-bit number. Consider the number of ones. The number of ones are 1 and 2. Consider another 4-bit number. Consider count the number of ones. There are 3 ones. So similarly, we'll have to do that. In a 32-bit number, we need to count the number of ones that are there in its binary representation, of course, and we need to save the result in R4. So let's move ahead. So we want to have a loop. So what is the idea? The idea is that in a 32-bit number, each of these bits needs to be considered one after the other. We need to check if it's a 1 or not and increment a counter. So essentially, if there is a loop, we need an index. So let's have an index variable. Let's map it to R2, initialize it to 1. Similarly, let's have a count variable, which is mapped to R4 because the final result needs to be saved in R4. So let's take a count variable, save it in R4, and initially the count starts with 0, right? Because we have not seen any 1 yet. So the first task would be extract the least significant bit and compare, right? Extract the LSB and compare. So in this case, how do we extract the LSB? So what we can do is that let's take the original number which is stored in R1 and let's AND it with 1. So in this case, all the upper 31 bits will get erased and only the LSB will remain. So in this case, the result of the AND will stay in R3. Let us now compare R3 with 1. Here is the new instruction that we insert over here, and it is very important to understand this part, that only if the comparison results in an equality, or alternatively, only if the LSB is equal to 1, do we increment the count, which is in R4, by 1. Alright, so only if the LSB is equal to 1, we increment the count by 1. Otherwise, this instruction works as if it has just never been seen or never executed, right? So in this case, we are essentially counting if this LSB is 1. If it is 1, we increment R4. Now let's prepare for the next iteration. So what we do now is that we take the number R1 and we do a logical shift right. Mind you, not an arithmetic shift right, because in this case we don't want to replicate the sign bit. So we shift it right by 1 position and we save it back in R1, and simultaneously we increment the index. So R2 we increment it with 1. So then once the index reaches 32, so I'm sorry, so then we compare. So we start with the index of 1, so basically 1 to 32 times we need to loop, but once it is 33 we need to get out. So we compare R2 with 32. If R2 is less than equal to 32 BLE, then we go back to the original looping instruction, otherwise we come out, and the final result is saved in R4, which is the count. So the important point to understand for all of us is this add EQ instruction, which made our life extremely easy. And the add EQ instruction pretty much, otherwise we would have had to have a branch. We would have had to, after this point, if the comparison is successful, we had to add a branch statement where we either increment it or don't increment R4. But that entire piece of code was folded into this one single instruction, which makes our coding process very, very efficient. Now that we have seen basic instructions, advanced instructions, and branch instructions, let's move to memory instructions. So similar to simple RISC, ARM has a very basic load instruction, which is load R1 with a register indirect operand R0. So in this case, the address, the memory address is stored in R0. We read it, we access memory, read 4 bytes and save it in R1. Exactly the same as simple RISC. And similarly, the store instruction works in a very similar fashion. Here the idea is that instead of reading from memory, we write to memory. The address is contained in R0. So we use the address to access memory. Then we take the contents of R1 and store it in memory. But as luck would have it, life is not that easy. So ARM has many kinds of complicated variants of memory instructions. So let's at least attempt to study most of them in this particular chapter. So ARM also has a base index kind of mode where we use the basic LDR instruction, the load instruction, to load the value of the address, to essentially load the value of the bytes that are stored at this memory location, R0 being the base register and 4 being the offset. So I'm sorry, it's not a base index mode, it's a base offset mode. And so in this case, 4 is the offset that is being added to R0, and then this is being saved in R1. So it's a base offset mode of addressing. And similarly, we can have a base register and we can have an index register. So in this case, what we do is that so essentially the address of the load instruction is supposed to be between these two square brackets. So this particular instruction is working as follows, that into R1 we are saving the contents in memory, where the address is given by R0 being the base register and R2 being the index register. So we take their contents, we add the contents of R0 and R2, we come up with an address and use that address to access memory and read in 4 bytes. So let's take a look at all kinds of addressing modes that are possible in ARM. So load and store, the addressing modes are very symmetric, so we'll only consider the case of load. So we can have a regular register indirect mode, which is of the form LDR R1 square brackets R0, where we take the contents, so the memory address is given in R0. We have a base offset mode. In this case, the base register is provided and the offset is provided. So we take the contents of the base register and we add 4 and we save it in R1. Similarly, we have a base index mode which is R0 and R2. So we just add the contents of R0 and R2 and access memory, save the bytes in R1. Then we have this mode which is slightly complicated. So this is a base register. So R0 is still the base, but we have a scaled index. So in this case, we are shifting the index to the left by 2 positions. So that's the reason I have the left shift operator over here. So this is the base scaled index mode, which is useful for accessing arrays and so on, because typically we would access arrays if we access them element wise, like 0, 1, 2, 3, 4. In terms of bytes, if each element takes 4 bytes, so they need to be accessed as 0, 4, 8 and so on. So we can take the sequence 0, 1, 2 and multiply it by 4 or left shift it by 2. So this is where the notion of the base and scaled index comes in, where so the portion of text within the square brackets denotes the address, and the way that the memory address is computed is as follows. It is R0 plus R2 multiplied by the left shift amount or divided by the right shift amount. But let's say it is R2, in the case of a left shift, it is LSL hash 2, which means, so this R2 LSL hash 2 is a shifter operand, and so instead of LSL we can have LSR, ASR and ROR. So all 4 of those shifts are allowed. So in this particular case we have given LSL as an example. So in this case we are pretty much taking R2 and shifting it to the left by 2 positions. So in this case R0 is the base, R2 is the index, and we are scaling the index, which means multiplying the index by 4, which is the same as left shifting it by 2 positions. As discussed in the last slide, let me explain a small example with arrays. So let's first take a look at the C program on top. So in this case, the input is an array of 100 elements. So we have a sum and we have an index. So the idea is to add all the elements in the array. So in this case, the index moves from 0 to 100. So we iterate through all the elements in the array, and we do sum equals sum plus AIDX, which essentially means we are adding all the elements of the array to the sum. So the final output will be there in the sum variable, and the sum variable can be returned as well, but I'm not showing that. So in ARM assembly, the first task is to first map the variables to addresses. So in this case, sum is equal to 0, which means that the sum variable is mapped to register R1, and register R1 is set to 0. So this is also the starting point in the C program, and we set our index equal to 0 and we map index to register R2. So the first thing that we do is that we need to load from memory the value of the first array element. This can be done very easily. So since we assume that the base address of the array is in R0, so we use this as the base register. Then we use a shifter operand where R2 is the index, and we essentially compute R0 plus R2 times 4. The reason 4 comes is because one integer is 4 bytes and we are accessing memory at the level of bytes. So we'll take one register R2 which contains the index, multiplied by 4, which is the same as shifting it to the left by 2 positions. So R2 LSL hash 2. So this gives us the address of A IDX. We read the value from memory and put it in R3. Then we increment the index, add R2 hash 1. and we compute sum plus equal to a idx. Uh, so actually we should be having a comment over here. So basically the comment should end. So sum plus equal to a idx. So in this case, we take the current sum, which is in R1. We add R1 with the value that we read from memory, which is R3. After computing the sum, we compare the index, which is in R2, with 100. So if you have reached 100, which is basically if you have reached 100 over here, the loop terminates. So if you have not reached 100, so if it's branch not equal to, which means R2 is not equal to 100, which means we have more iterations left. So we go back to the beginning of this phase, which is dot loop. So here, let's count the number of lines of code in C. It's 1, 2, 3, 4, and actually we should count the closing brace as the fifth line because it's essentially taking us to the beginning of the for instruction. So let's say, depending upon how we count, it's 4 or 5 lines of code. The number of assembly lines is 1, 2, 3, 4, 5, 6, 7. So 4 or 5 lines are converting to 7 lines, which is actually not all that bad. And the reason that we were able to have such an efficient assembly representation is only because of this LDR instruction over here, which allowed us to access the contents of memory for an array very easily, because the address here we are being we have a very easy way of computing R0 plus R2 times 4 in a single expression, where we can specify the base register, the index, and what the index should be scaled with, which in this case is 4. So this is what enabled us to write nice and compact code. Now let's take a look at even more advanced memory instructions. So consider an array access again. So I'll just take out the relevant instruction. So maybe if I just go to the previous slide, this was the instruction that was being used to access the array. So I can again come back over here and have load R3. I'm just repeating the array accessing instruction. So we have this, and subsequently we increment the index, which is R2. So this is a very common pattern. So whenever we access an array, we'll most likely access it within a loop. And so the typical pattern would be that we access an array element and then increment or decrement the array index. So we should have a way of fusing both into one instruction, which in this case would imply that we have to sort of tell the processor that after doing this increment R2. So let us have a method of doing it. So in this case, so ARM defines a new format, where the format is like this, that we write LDR R3 and we sort of move the end of the square bracket to, so instead of encapsulating the entire thing, we move the end of the square bracket to just after R0. So we'll have LDR R3, R0, which is the base address register within a square bracket, and then the index and the scale amount and the shift amount, right? So the only change is that the square bracket has moved its position. So it has pretty much moved from, I would say, this position to this position. That's the only change. So this is a new kind of assembly instruction format that we are introducing for the LDR instruction. So this is equivalent to set R3 as the contents of R0, and subsequently you compute R0 is equal to R0 plus R2 times 4. So this is what this particular instruction is equivalent to. It's called a post-index addressing mode. Right, so basically the so what is this code snippet over here equivalent to? It's equivalent to that we first read the contents of R0 into R3, and then we compute R0 is equal to R0 plus the contents of the shifter operand, which is R2 left shifted with 2. Similar to the post-indexed addressing mode, we have a pre-indexing addressing mode as well. So post-indexing is something similar to I++ in C and C++. So pre-indexing is something similar to plus I, right? So where we increment the value first and then proceed with the current instruction. So the format over here is something like this, that we will have LDR. So this part is common. Then we specify the address. So the address can take any format. We can either have the register indirect mode, base offset mode, base index mode, base scaled index mode. It doesn't matter. But the important point is we need to add an exclamation mark at the end. So this will essentially tell us that we need to go for the pre-indexed addressing mode. And this is equivalent to, we are accessing, so basically this is equivalent to the fact that we access the memory at this point R1 plus 4, right? It's equivalent to that. That we first add 4 to R1, compute the address and access the memory at that location and save the result in R0. And we also increment R1 to R1 plus 4, right? So both of these are done. So the difference, had this been post-indexed, you would have accessed the memory only at location R1. But since it is pre-indexed, we increment R1 first, use the incremented value to access memory. So if I would write equivalent C code, this is what it would look like. Equivalent, pseudo code, that we access the memory at the augmented location of R1, which is R1 plus 4, and also then we increment R1 to R1 plus 4. Now that we have seen the pre and post indexed addressing modes, which is very similar to I++ and ++I in C, it's time to see how we can use them. So let's go back to our example where we were essentially adding numbers. So this example is as follows, that, okay, let me again correct it with the end of the comments. So we're adding 100 numbers. We're adding 100 numbers in a loop, and we use this complicated expression over here to pretty much compute R0 plus R2 times 4. Times 4 is same as left shifting it by 2 positions. So R2 contained the index, so this gave us the address of the element in the array, where R0 is a base register. So the address would increase as follows: 0, 4, 8, 12, 16 and so on. Alright, so now let's go back and take a look at the same example with slightly reduced code. So before looking at the example, I just want to stress once again that I++ is the pre-indexed, I++ is the post-index mode, similar to what is there in Java C, C++. And ++I is the pre-indexed mode, right, where we first increment the variable and then use it. Alright, so let's take a look at an example with arrays. The same example, adding the first 100 elements of an array. So basically, let's see. Our aim is to use either a post-index or a pre-index addressing mode. So in this case, we shall use the post-indexed addressing mode. So let's start. So first thing that we need to do is register assignment. So we take our sum variable, and so which is supposed to contain the final sum, and we initialize it to 0. So this is common. This is something we have to do. But here is something that we want to do. We want to eliminate the index from our computation completely, from our assembly program completely. So, we don't want to use the index. We want to rather use the sophisticated addressing modes. So let's do one thing. Let's compute the end of the address of the first byte that is at the end of the array. Right, the first byte, which is actually illegal. So if you consider this as the memory region that contains the array, let's consider the first byte, which is not in the array and is just outside it. So this is essentially, so since we have 100 elements in array A, the elements are from A0 till A99. and pretty much A100 is an illegal element. So the address of A100, the starting address, would be the first address after the end of the array, and this will be A plus 100 times 4, because one integer is 4 bytes, so this is A plus 400. So let's do that. Let's take the value of the base address R0. Let's add 400 to it. So essentially we're setting R0 to the address of A100, and we save this in R4. Alright. So we are actually not setting R0, this should be, we are setting R4. Right. So let me just fix this, is not correct. So we are setting R4 to the address of A100. Alright, which is an illegal address. So let's do one thing. So this is essentially all the greatness of ARM pretty much lies in this instruction, which is the first instruction, where so R0 contains the base address, so we start and access R0. The value is transferred to R3. Subsequently, we increment R0 by 4. So all of this will be done by this instruction. So what this instruction would do is that it would set R3 to the contents, the memory contents, where the address is in R0, and then it would set R0 equals R0 plus 4, and this is the crux of the post increment instruction, that both of these things will happen within the same instruction, where the instruction is LDR. So in the LDR, the load instruction, we shall load the value, this value the value from memory whose address is contained in R0. Then we shall increment R0. Subsequently, the value that we read, we shall add that to the sum. So this is same as computing sum plus equals AIDX. And here what we do is, since we are incrementing R0 in every iteration, we just compute the fact if R0 has reached R4 or not, which essentially means R0 we are treating it as a moving pointer, which is first pointing to the first element, then the second element, then the third element, till it reaches the end of the array and sort of goes out of it. So we compare R0 with R4, where R4 is an illegal address. So if R0 is equal to R4, then clearly we need to exit. If it's not equal to R4, we need to come to the loop over here. So if we'll compare the previous, so let's again quickly go back and count the number of lines. So the number of lines before the loop is not important, mainly because the loop will actually heavily overshadow the number of lines before it. The loop runs for 100 times, and each iteration of the loop has 5 instructions. So pretty much we'll have 500 instructions in the loop. But if we come here, we see that each iteration of the loop actually has 4 instructions. So we'll have a total of 400 dynamic instructions, which is a healthy savings of 20%. Right? So we are able to reduce our number of instructions by a fifth by using this post-indexed addressing mode. So both pre-indexed and post-indexed addressing mode can be used for the load instruction and the store instruction as well. All of these examples are with the load instruction, but they can be done for the store instruction as well. Now let us discuss some of the memory instructions that are used in functions. So you often see that it is necessary to store a set of registers before calling a function, and it is necessary to restore them. So this code to store registers is called spilling. So we have two schemes, caller saved and callee saved. In both the schemes, we spill a set of registers, which means save it on the stack, and then once we return from the function, we restore the set of registers. So we typically require several instructions to spill the set of registers and restore them. So ARM has made this job easy. So there is one instruction, stmft, for spilling a set of registers and essentially saving it on the stack. Saving not it, but I would rather say them. Similarly, we have the ldmft instruction to restore a set of registers. The format of both the instructions are roughly the same. So we first specify the stack pointer. Then similar to the pre-index addressing mode, we have an exclamation mark. So the exclamation mark is basically to say that at the end of the instruction, the next instruction should see an updated stack pointer. For example, if you push in 3 registers, then at the end of the instruction, we should see the stack pointer subtracted by 12. So let's maybe consider the STMFD instruction first. So here we push the registers on the stack in descending order and we update SP. So let's take a look at this descending order. Let's assume that we want to push the values of registers R10, let's say R4 and R10. So what the hardware would do is the hardware would first sort them in descending order. So it would be R10 and then R4. The values of these registers would be pushed in the same descending order. So R10 will essentially be pushed first, assuming the stack is downward growing, R10, and then we would push R4. So the LDMFT instruction does exactly the opposite. So what it does is that it starts at the top of the stack and pops the stack and assigns values to registers in ascending order, which is the reverse order. So first you would pop R4, then it would pop R10 and update the value of the stack pointer to what it was before. We shall find both of these instructions, LDMFT and STMFT, to be extremely useful when we discuss, when we show an example of how to use them to save and restore registers. So here is the example. So the idea is like this, that let's write a function in C and implement it later in ARM assembly to compute x to the power n, where x and n are natural numbers. So assume that x is passed through R0 and n through R1, and the return value is passed back to the original program via R0. So I'll not show the C code, but the C code is easy to write. So essentially, if we have a function of the form power int x and int n, we first want to check if n is equal to 0, we would return 1, because any number to the power 0 is 1, so we return 1, else we return, so the C function is very straightforward actually, else we return x times power x n minus 1. So this is just a simple function in C that we have. So I'm not, it's a simple one-line function, so I'm not further spending time to explain it. So the idea is that if the power of n, if n is equal to 0, any number to the power 0 is 1, so we return 1. Otherwise, we return x times the power function x to the power x times x to the power n minus 1. So now let's take a look at how to implement it in ARM assembly. So we can first implement the first line, which is compare n with 0. Since n is stored in R1, we compare it with 0 if there is an equality. So basically, if there is so we use a predicated or a conditional instruction over here, that if n is equal to 0 and equality holds, then we will execute this instruction move eq, which will move 1 in R0, which is our return value. Similarly, if there is an equality, we will execute the bx instruction and we will jump to the return address. So mind you, these two instructions are conditional instructions. So if there is an equality found in the compare, these two instructions will execute. Otherwise, the hardware will just convert them to no ops. So the nice thing of using conditional instructions is that we avoid branches and so on. So it makes our code look very neat and straightforward. Subsequently, So in this particular approach, what we are doing is that we are first saving the values of the registers that we will most likely change, and then we go on and we do our changes. So think of this as primarily a callee saved scheme, because here if we assume that this function is a callee, then we save all the registers that the caller might require, and also the registers that we'll modify, and then we proceed. So basically, since it's a recursive call, definitely the return address register will get overwritten. So we save it. Along with that, we save a temporary register R4, because this also will get overwritten. So we save R4 and LR in the stack pointer using the STMFD instruction. So we save them on the stack. Subsequently, we move the value of X, which is in R0, to R4. The main reason for doing this is that R0 is also carrying a return value. So in general, in the ARM ABI is Application Binary Interface, the convention is that return values typically come via R0, and the arguments are typically passed in R0, R1, R2, and so on. So since R0 is being used both as an argument as well as a return value, before calling another version of the power function, we have to save R0 in another register, let it be R4. Subsequently, we subtract R1 by 1 because R1 contains n. So this is equivalent to n equals n minus 1, and we call power. So mind you, in the power function, what are the arguments that have gone? The arguments that have gone are x and n minus 1, and the final result of the power function is in register R0, which contains x to the power n minus 1. We multiply this with R4, where R4 contains x. So x times x to the power n minus 1 becomes x to the power n. Subsequently, we need to, so since this particular approach is a callee saved approach, what we need to do is that we need to restore the values of the registers that we have modified. So R4 is something that we have modified, so we need to restore it. And similarly, well, LR we have modified, but we don't have to restore it. We have to do something else. So, so this instruction is actually slightly tricky, but let me explain how it works. So let's first consider the case of R4. So as I had said, we save these in descending order. So essentially, if this is the stack which is downward growing, so this is the stack top, we first have R4, and then we have the value of LR. Now when we execute the LDMFD instruction, we'll pop the registers in ascending order. So R4 will get popped out and will get assigned to R4, which means that the value of R4 is getting restored. Now here is the trick. So basically, we have LR over here, but when we next pop out LR, instead of saving it in LR, we actually save it in PC. So mind you, this is the trick. So let me put a star over here. So this is same as moving the contents of LR into PC. So this is exactly the same as move LR into PC, which is exactly the same as returning from the function. So as you can see, we are achieving multiple objectives, essentially killing two birds with the same stone. We had modified R4. So as a result, just before returning, we are restoring the value of R4 so that the caller will not be able to know. Secondly, LR is something which we had modified, so that's we later on modified. So that's the reason we saved it on the stack. But now when we are returning, there is no real justification of actually restoring LR, because in any case it makes little sense to restore it after the function has returned. What we instead need to do is we need to effect the return. So we essentially pop the value of LR, but instead of saving it in LR, we save it in PC. So this has exactly the same effect as move LR into PC or essentially return from the function. So this is a very standard way of writing ARM code where we have a matching STMFD and LDMFD instructions. So it will restore all the values of the registers, but instead of restoring the value of LR, what we do is we pop the value of LR and put it in PC. So this is tantamount to returning from the function. So this little piece of code, so actually if you take a look at it, this C code has essentially two statements inside it. And in terms of assembly code, it's actually fairly complicated. So it turns 3, 4, 5, 6, 7, 8, 9 statements. But actually it could have been actually much more. We reduced it by using tricks in the ARM ISA. So one trick that we used is that we used the EQ suffix, the EQ condition, to ensure there are no branches, and we put in a predicated instruction there. So that took care of the base case. To take care of the recursive case, we decided that we have to call other versions of the power function. So to call other versions of the power function, we have to save and restore some registers, because particularly register R0 is containing an argument and is also supposed to contain the return value. So what we do is, so we again have two options, caller saved and callee saved. So had we done a caller saved kind of approach, that would have also been fine. Have a caller saved approach, we basically see that what are the registers that the caller would actually require, and we save those registers. So the registers are essentially R0 and LR that the caller will require. So we should have saved them and then again restored them after the power function. In a callee saved approach, the idea is slightly different. In this case, what we essentially do is that we find out what are the registers that the callee is actually modifying, and we save them at the beginning and restore them at the end, such that the caller is not able to find out what the callee did. So in this case, R4 and LR are registers that we save because we'll modify them later. And again, while returning from the function, we restore R4, and instead of restoring LR, we pop it out but put its value in the PC, which is same as returning from a branch. Let's now look at ARM instruction encoding. So here the basic problem is that we need to encode instructions in a bit field of 32 bits. So let's first define the generic format which most of the ARM instructions follow. So here the first 4 bits, 29, 30, 31 and 32, these 4 bits represent the condition. So we had talked about 14 condition codes in a previous slide. So these condition codes for EQ, NE, GT, LE and so on. So all of these condition codes, since there are total 14 of them plus the AL condition code, which means always, so 15 of them, we need 4 bits to encode them. So the top 4 bits of the encoding encode the condition code. The next 2 bits encode the type of the instruction. Since we have 2 bits, ARM can support mainly 4 broad types of instructions. So we'll see what the types are in the next few slides. So let's consider the generic format of data processing instructions, which are basically ALU instructions, arithmetic and logical instructions. So let me write it. So let's consider the first 6 bits. So they follow the generic format. The first 4 bits is the condition, and 00 is the type of the instruction, type 00. Subsequently, the I bit or the immediate bit indicates if the second source operand, so this is the second source operand, if this is an immediate or it's shifter operand. Essentially, if is it a register shifted by a certain value, or it's an immediate. So this is specified by the I field, the immediate bit. Subsequently, the next 4 bits specify the op code or the operation code, what kind of operation it is, such as add, subtract, logical AND, logical OR, and so on. The 21st bit is the S bit. So the S bit is the S suffix bit that we talked about. So for example, we talked about the instruction add S. So the add S instruction sets the CPSR flags, the program status register flags. And so this is the S suffix. So this can be added to any data processing instruction. This will automatically make it set the CPSR flags. Subsequently, we have the ID of the first source register. Since there are 16 source registers, we need 4 bits to encode them. So this is the ID of the first source register. Then this is the ID of the destination register, RT. And the last 12 bits are reserved to specify either a shifter operand or an immediate. So encoding immediate values is kind of tricky in ARM. ARM has 12 bits for immediates. So 12 bits, 12 is a bad number. It's not 8, it's not 16. So it is essentially not 1 byte, nor is it 2 bytes. So let us divide 12 bits into 2 parts or 2 fields. So let one be an 8-bit payload and other a 4-bit rotation value. So we'll see what these are. So the real value of the immediate can be calculated like this. So let's again consider the 12-bit field. So the 12-bit field over here is being divided into a 8-bit payload. So the 8-bit payload is basically 1 byte of information and a 4-bit field called rot. So the way that the immediate is calculated is like this. So consider an ARM instruction which is encoded in a bit field of 32 bits. In the ARM instruction, the least significant 12 bits are encoding an immediate. So what the processor would do is that the processor will essentially expand this 12 bits to a 32-bit quantity inside. Right? So actually even before that, when I specify an immediate in assembly code, right? So consider this as assembly code. When I specify an immediate, the assembly code would try to convert it, encode it into this 12-bit form, if it is possible. So we'll discuss this later. Subsequently, once this has been encoded in 12 bits, once this actually executes, what the processor will do is that it will take these 12 bits out and expand the 12 bits into a 32-bit quantity. The way that the processor would do it is as follows. It will take the 8-bit payload and rotate the payload with a number which is 2 times ROT. So let's consider an example. So let us consider a hex, 2 hex digits. 1 hex digit is 4 bits, so 2 hex digits are 8 bits. So let us consider a 32-bit number and let's consider a payload of the form, let's say FE. Now let's say that the value of the rot field is equal to 2. In this case, this number needs to be right rotated by 4 positions. So right rotation basically means that all the bits in the LSB position come to the MSB position. So if I right rotate a number by 4 positions, it basically means that 4 bits from the LSB come to the MSB. And 4 bits is 1 hex digit. So what this will essentially become is E0, 0, 0, 0, 0, F. So similarly, I can encode a lot of immediates and figure out their actual value. So the actual value that the processor would use. And the standard formula is this one, that I take the 8-bit payload and I right rotate it with a value which is 2 times ROT. So ROT, since it's a 4-bit number, it can be between 0 to 15. So 2 times ROT can be between 0 to 30. So one thing that is obvious is that if I take a number and I right rotate it by 32 positions, then again the number, the 32-bit number will become exactly the same. So you can see if one bit is right rotated by 32 positions, it'll come, again it will reach its original position. The same is true for all the bits. So any number, any 32-bit number right rotated by 32 positions is equal to the number itself. So essentially 32 is a limit, but what the ARM format is saying is that it allows you to specify 8 bits and further a right rotation such that you can rotate it by any number which is in the range of 0, 2, 4, 6, just even numbers till 30. So this sort of, the intuition behind this is like this. That's, look, we have a limited number of bits in the instruction format. We only have 12 bits. So 12 is a bad number, it's not 8, it's not 16. So what is the best that we can do? We can specify 1 byte of information, but the additional 4 bytes also give us a handle of saying where that 1 byte will be located. Right? So basically at which position, at which even position that 1 byte will be located. For example, it is very easy to encode a number of this fashion in the ARM ISA. So what is this like? So this is basically, I have FE over here and I right rotate it by certain number of positions till it sort of reaches over here. So how many positions would this be? If I right rotate FE by 8 positions, it will reach here. 16 positions, it will reach here. 24 positions, it will reach here. So basically, FE, I can consider 0x FE right rotated, ROR 24 is essentially this number over here. So that its encoding would basically be, so 24 divided by 2 is 12. So its encoding will basically be, the ROT field will be 12 C FE. Right? So this is the encoding of the immediate field. So as we can see, the notion of immediates is slightly tricky in ARM. It is actually not very simple. But in any case, it is definitely possible to encode a lot of numbers with this. So the first thing is that when the programmer or the compiler, they write an assembly instruction with an immediate, for example, let's say 4, the job of the assembler is to convert it to a 12-bit format if it is possible to do so. If it is not possible to do, for example, a number of this form, just has too many bits, so it is not possible to specify it in the 12-bit format, so multiple instructions are required. But in any case, if it is, we use multiple instructions, each of the instructions specifies an immediate which can be put in this format, and the assembly code is created. Subsequently, when the processor sees this instruction, it takes the 12 bits out and expands them to 32 bits. How would it do it? It would basically take the field of 12 bits, divide it into two parts, the ROT and let's say the payload P. It will then take payload and right rotate it with a number which is 2 times ROT. This will give us a 32-bit number which the processor will internally use. So let's look at the explanation of encoding in slightly layman's terms. So the payload is an 8-bit quantity and a number inside the processor or a number in a register in any 32-bit processor is a 32-bit quantity. So since the payload is 8 bits, we can only set 8, preferably contiguous bits in the 32-bit number at the time of specifying an immediate, right? Only 8 bits can be set. The additional choice that ARM assembly is giving us is that we get to choose which 8 bits these are, right? So how many bits are left out of 12 bits if this is the 8-bit payload? The choice that ARM is saying is that, look, you have 4 more bits, do whatever you want. With 4 bits, what can you do? You can encode any number between 0 and 15. So since in general we'll not place numbers at odd positions, starting at odd positions at least, ARM says that multiply this by 2. So then the range will be, so numbers will be of the form 0, 2, 4, 6, 8 till 30. So you take this 8-bit number and place them at any of this position by right rotating it. So the starting point of this sequence is an even number, and ARM gives us some amount of flexibility to actually do this. So this is actually a fairly complicated aspect of the ARM ISA. So I would request all the readers to spend a lot of time in understanding this particular aspect. So the book has a lot of examples and has some amount of explanation also with regards to this, but my request to all readers is to understand this part at least very, very well. So let's look at some examples. Encode the decimal number, let's say 42. So 42 in the hex format is 0x2a, 2 times 16 plus 10. Or alternatively, if I want to make it a 32-bit quantity, we can put 3 bytes before it, all zeros. So since there is no right rotation involved, the immediate field is 0x02a. Now let's encode the number 0x2a 000. The number is obtained by encoding 0x2a by actually 8 positions, by actually right rotating 0x2a by 8 positions. So basically the intuition is that to move one hex digit it takes 4 right rotations. So to move 2 hex digits it'll take, so to move a hex digit by actually 2 positions, 2 places, it'll take 8 right rotations. So the number of right rotations is 8, we divided that by 2, we get 4. So the encoding of the number is 0x42a. So similarly we can have all kinds of numbers and we can try to encode them. So these can actually be thought as trick questions, but the main idea is that ARM immediates are slightly tricky, and it needs to be kept in mind that we are only setting 8 contiguous bits, and so essentially that's the trick, that 8 contiguous bits inside a 32-bit number are being set, and their starting position can be varied using the ROT field. Alright, so let's now look at encoding the shifter operand. So basically, if you are not using an immediate, yet we are using a register that can possibly be shifted, then let's look at how to do it. So we have 12 bits. So so there are essentially two options. So one option is that um, we are actually shifting a register by an immediate value. So this register is specified as the lower 4 bits. This is called register RT. And the fact that we are shifting it by an immediate value is encoded in the next bit, which if it is 0 means we are shifting it by an immediate value. So the shift type, so we have 4 kinds of shifts in our ARM ISA: LSL, LSR, ASR and ROR. So these 4 shift types, since there are 4, they can be encoded with 2 bits, with LSL being 00 and ROR being 11. So the shift type is encoded in the next 2 bits, and subsequently is the shift amount. So any number can only be left shifted or right shifted or rotated by at the max of 32 positions. So we need 5 bits, which is exactly what we have. So that's lucky for us. Let's now consider the second variant. In this case, we again have the RT register, which requires 4 bits. But instead of this number being 0, the 5th bit, the 5th bit is 1, which means that we are actually shifting RT by the value in a register. So the shift type is encoded with the next 2 bits, and the top 4 bits encode the ID of the register, which contains the shift amount. So let's now discuss LoadStore instructions. So LoadStore instructions are also follow the same generic format. So the first 4 bits represent the condition, the particular all the 16 conditions that we have seen. In this case, the type of the instruction is actually 01. So this is the type of the instruction 01. And subsequently, we have 6 bits I, PU, BWL, which I'll discuss subsequently. So then, so RD in the case of a load instruction is the destination of the load, and RS is the base register. So in the case of the store, they maintain a similar connotation. RS is still the base register, and RD is the register that the value comes from. And the most important thing is that immediates in the load store format are not in the rote plus payload format. Instead, they are standard 12-bit unsigned numbers, right? This is an important distinction to keep in mind, that these are standard 12-bit unsigned numbers, and they are not in any special format, neither are they signed numbers. So what we need to discuss now is the connotation of these fields I, P, U, B, W, L. So the I bit, basically if it is 0, it says that the last 12 bits represent an immediate value, right? A fixed offset from the base register. And if it is 1, it says that the last 12 bits represent a shifter operand. So that's the I bit. So the connotation of the I bit can slightly change. In one case, if I is 1, it represents an immediate, but that is the connotation in this case. The P bit, if it is 0, it represents the post-indexed addressing mode. If it's 1, represents the pre-indexed addressing mode. The U bit says that if the U bit is 0, we subtract the offset from the base, otherwise we add the offset to the base register. If the B bit is 0, we transfer a memory word, which in this case is 4 bytes, or we transfer a single byte, which is 1 byte. Similarly, if the W bit is 0, it says that use regular addressing, don't use pre or post indexed addressing. So W can be thought of as the write back bit, where essentially the base register is changing. And if W bit is 1, means that use pre and post indexed addressing. Lastly, how do we differentiate between a load and a store? Well, that's very simple. So if the bit is 0, means we store to memory, so L can be thought of as the load bit. And if the bit is 1, we load from memory. Lastly, let's take a look at branch instructions. So in the case of branch instructions, we have this exactly the same generic format. So we have the 4-bit condition, and actually the type of the instruction is 1, 0. So that is the type. There is a further 1 bit for the subtype, which for at least most of the common instructions is 1. Subsequently, we have the L bit or the link bit. So with the link bit, recall the BL instruction. Say the link bit is 1, it basically means that the return address register is set. So we are sort of looking at a function call. And subsequently, we have a 24-bit offset. So this is the branch offset, very similar to simple RISC. And also similar to simple RISC, this is not the offset in terms of bytes, it's the offset in terms of memory words. A memory word is defined as 4 bytes in this case. So the offset, so let's call it the byte offset, is equal to the offset specified over here multiplied by 4. This is very similar to simple RISC, because the idea is if we assume that every instruction starts at a boundary of 4 bytes, then the last two LSB bits are 0 and 0. So there is no need to specify an offset whose last 2 bits are always constant. So instead, let us specify the offset in terms of memory words. So we'll essentially save 2 bits in this case. So for the branch instructions, what does the processor do? It expands the offset to 32 bits with proper sign extensions. It shifts it to the left by 2 bits because it's in terms of memory words. And it adds it to PC plus 8 to generate the branch target. So before you ask me, let me tell you why PC plus 8. This is sort of non-intuitive, right? But we are not in a position to answer this. You need to wait till chapter 9 for the answer to this question. Alright, so this brings us to the end of the beautiful chapter on ARM assembly. So I'll see you in the videos for chapter 5, which are on x86 assembly.